We are in section 4.3, complements, conditional probabilities, and Bayes' theorem. Computing at least probabilities typically uses the complement rule. The phrase at least means greater than or equal to. So if you say you want at least one, that means one or more. So at least one means that the probability of at least one occurrence of event A, or another way to think of this is if you say at least one would be one or more. You're considering everything except for having none of those. So you would do 1 minus the probability of no occurrences of event A. So we have an example right below this. And the example says, among Americans who consider themselves avid bakers, 59% say their favorite item to bake is cookies. So 59% say their favorite item to bake is cookies. Suppose that 4 avid bakers are randomly selected. Part A says, what is the probability that all 4 will say that their favorite item to bake is cookies? First of all, when we're dealing with people, almost always they are going to be independent of one another, meaning that one has no effect on the others in their favorite thing to bake. Sometimes we will have issues where people will be dependent, and those kind of situations would be if you are looking for a sibling and it's dependent upon the other person that you select, or a twin, or a spouse, or maybe mother child or father child, something along those lines. But for this case, we are dealing with people and they are independent of one another. So part A says, what is the probability that all 4 will say their favorite thing to bake is cookies? So all 4 favorite thing to bake is cookies. And so this is going to be the probability that the first person says that their favorite thing to bake is cookies, and that is 59%. I'll write that as a decimal. The second person, same chance. And again, because these are independent, we're using that multiplication rule for independent events and multiplying these all together. The third person would be also the same, and then that fourth person would also be the same. Another way to write this is 0.59 to the 4th power. So you can definitely do that on your calculator to make it go a little quicker. But multiplying this out, rounding 4 decimal places like we normally do for probabilities, we get 0.1212. Part B says, what is the probability that none will say that their favorite thing to bake is cookies? So this is going to be the probability that all 4 not favorite is cookies. So to figure out if the first person prefers to bake something other than cookies, we would have to do 1 minus 0.59, which was the chance that their favorite thing to bake is cookies. And we would get 0.41. And so again, we would do this for the first person. And again, for the second person, it'd be 0.41. The third person, 0.41. The fourth person, 0.41. So yes, you can write this 4 times. Or like we said earlier, you could just raise this to the 4th power. Substituting this all into your calculator, rounding your answer to 4 decimal places, the probability would be 0.0283. So the next part, part C, says, what is the probability that at least one, so here's that at least one that we just discussed up above, will say that their favorite item to bake is cookies. So probability that at least one favorite thing to bake is cookies. And so what this means is 1 or more. So either 1 says their favorite thing to bake is cookies, 2 people, 3 people, or 4 people, all 4 of them. So one way to do this is to figure out all those different situations and add them all up. But take into account that, in fact, that, when you say the first person, one person likes it, it could be the first person or the second person or the third person or the fourth person, and you have a lot of different situations here. The one situation that we're not looking at for this, because it says at least one, was 1 or more, is going to be the probability that nobody likes to bake cookies. So all 4 of them say nope, not cookies. So in order to figure this out, I'm going to do 1 minus that case that we're not considering to get the final probability of at least 1 says that their favorite thing to bake is cookies. So this would be 1 minus the probability that all 4 not favorite thing to bake is cookies. And we actually came up with this right up above. So that was 0.0283. And so the probability that at least 1 out of these 4 avid bakers will say that my favorite thing to bake is cookies would be 0.9717. So pretty high chances. The next example says the table below shows results from a chem bio test for hepatitis C among HIV infected patients. You can see that there's positive test results, negative test results, and then those who were tested who actually had hep C and those who did not have hep C. You can see we have false positives and also false negatives. And so for this, part A says find the probability of selecting a subject with a positive test result given that the subject does not have hep C. Why is this case problematic for test subjects? And we'll talk about that in just a minute. So this will be the probability of having a positive test given, which you remember, conditional probability, that would be that straight up and down line. So given that the subject does not have hep C. So no hep C. And our formula for conditional probability stated that we can either say probability or number, and since we have numbers here, I'm going to go ahead and put a number sign. This will be the number of people who have both a positive test and no hep C. So, and no hep C divided by what was given. So the number of people that have no hep C. So the number of people who have a positive test and no hep C are going to be 2 divided by the total number of people who do not have hep C. And the total number of people that have no hep C, and I'll go ahead and put a total column over here, would be the 2 plus the 1,153. So that comes out to 1,155. Then dividing this and rounding 4 decimal places, we get 0.0017. There is a second question here for part A, and this says, why is this case problematic for test subjects? So again, it said find the probability of selecting a subject with a positive test result given that they do not have hep C. So this would be that someone does not have hepatitis C, however their test result says that they do. This is definitely problematic because you're being told that you have something that in actuality you do not. And this does happen. It doesn't happen often, as you can see with our numbers, but it does happen, and there is a chance of that for happening. The next part, part B, says find the probability of selecting a subject with a negative test result given that the subject has hep C. So again, this is another problematic one, but let's go ahead and say find the probability that they have a negative test result given subject has hep C. And so again, I'm going to use my number signs, and for that conditional probability with given, we're going to go ahead and say having a negative test and has hep C. So negative and hep C divided by the number of people total that have hep C. So the number of people who have a negative test but do have hep C is 10. And so that would go in our numerator, divided by the total number of people who do have hep C. And to get that, we would add the 335 plus the 10, which is 345. So that would be our denominator. And then dividing these, again rounding to 4 decimal places, we get 0.0290. So again, the chance of that happening is low. So next section that we have is section 4.4, which is counting. First thing is the multiplication rule for counting. If a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, and R selections for the third choice, and so on, then the task of making these selections can be done by multiplying them all together, and you get that in so many different ways. One example of this would be how many different sundaes can you come up with, maybe at like Yogurtland or a different frozen yogurt place. And maybe they have so many different options for flavors of frozen yogurt, and then they have so many options of fruit toppings and so many options of candy toppings and so forth. And so in order to figure out the different combos that you can have for a sundae and saying you could select one of each, you would just multiply all those different options together. And so multiplying these all together is how you would do this for multiplication rule for counting. So we have a first example on here. This one says, how many different current California license plates can be created using the standard setup? No special characters or spaces. Standard setup is going to be a number followed by 3 letters followed by 3 numbers. So the first thing is going to be a number followed by 3 things that are going to be letters, and then followed by 3 more things, and those are going to be numbers. And so in order to do this, we have to think of how many different choices there are for that first spot. So numbers, make sure you also consider 0. We have numbers 0 through 9, so technically there are 10 different numbers. And then letters, we have total of 26. They can repeat. This doesn't say anything about them not repeating, so you could have A, or B. So 26 would go in each of those. And then again, back to numbers, again, they can repeat. Doesn't say anything about you can't have 999 or something like that. And again, 10 numbers, because if you count them 0 through 9, there's 10 of those. So the multiplication rule for the different possibilities that we'd have would require us to multiply all these values together. Again, you get a very large number when we're counting, and this is 175,760,000 California license plates. So the next example that we have says a social security number is used to identify each resident of the United States uniquely. The number is of form, and there's 3 numbers, 2 numbers, 4 numbers. And it says where each X is a digit from 0 to 9. How many social security numbers can be formed? So again, if you were to put in each of those spaces a 10, because there's 10 different numbers, and you would have to sit there and multiply these all together, which is the same thing as saying 10 raised to the, and if you count all those spaces, there's actually 9 of those. And so we have 1 billion different social security numbers that we could have. There's a second part to this problem that says, what is the probability of correctly guessing the social security number of the U.S. president? And so this one says probability, and keep in mind that probability are going to be values between 0 and 1. Counting, when they ask for how many of something, it's usually a very large number, like we had 1 billion. And so if we guess correctly social security number of the president, the total number of social security numbers that we could guess goes in the denominator. We could guess a total of 1 billion different social security numbers. So that value would go into the denominator. And then the numerator would be the probability, would be the actual number of social security numbers that the president has. and we'd have to divide it to get the probability. So the social security number that the president has, we only have one of those. So dividing this, again, you're going to get a very interesting answer on your calculator, and you should get the 1e negative 9, which remember is the same thing as 1 times 10 to the negative 9th. Making sure to write it the correct way. The next part that we have is the factorial. And so a factorial is denoted with an exclamation mark. And this says if n is greater than or equal to 0 as an integer, then n factorial is going to be n times n minus 1 times n minus 2, and then so forth. So for example, if you had 5 factorial, this would be 5 times 4 times 3 times 2 times 1. And you'd be able to multiply this out. And then there's a little note at the bottom that says 0 factorial is equal to 1 and 1 factorial is also equal to 1. So right below this next example says 15 students in a class were asked to line up for a class picture. How many different ways can they line up? So if you think about it, we're going to have 15 different spaces here. And the class, every student sitting down, there's only 15 students total. And so the teacher's going to ask for one volunteer to come up and stand first. And she is going to only select one person, but total she can select from 15 different kids to stand up there. So now let's say Bobby is standing up at the front of the classroom. So how many students could she select from next? So yes, she's only selecting one, but she could select from 14 other students that are sitting down. So next, let's say she selects Carla. And so now Carla is standing next to Bobby. And then next, there's still 13 kids sitting down, and she needs one more, and she selects Jose, and then Jose is going to come up. And this process continues. And so we're going to have 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we're going to multiply these all together using that first rule that we had. And so another way to think of this is as 15 factorial. And so with this 15 times 14 times 13 and so forth, to do that on your calculator isn't too draining. But what happens if we had a senior class of 673 people and you're trying to figure out how many different ways there are for them to come up and stand? That's going to be a lot bigger of a number, and so that factorial allows you to kind of calculate it quickly. And so 15 factorial, and then in order to do this on your calculator, it's discussed below. And so you can see that we will look at that in just a moment down here. And so down below, you can go to math and then scroll over to PROB or PRB, depending on your calculator. And number 4 is our factorial. It might be something different on your calculator. Make sure you write that down. But when you work this out, so you can type in 15 times 14 times 13 and so on all the way down to 1. Or you can try to use the 15 factorial key that is discussed right below in the notes. And when you do this and you select enter, either way, you should arrive at a relatively large number. And the way that you can express this is usually it will tell you to round so many significant digits, or it might ask you to write it in scientific notation. I'm going to go ahead and write this in scientific notation, and I'm going to put down 1.308 times 10 to the, and if you count that out, it would be to the 12th. You get an answer of 1.308 times 10 to the 12th. And again, making sure that you write your answers correctly. The next thing that we have is a permutation and a combination. So these two we definitely need to know. So a permutation is the number of arrangements of R objects chosen from N objects in which the N objects are distinct, repetition of objects are not allowed, and order is important. It says AB is different from BA. And then it's given by, and we have a formula there. Now, likewise, combinations are the number of arrangements of R objects chosen from N objects in which the N objects are distinct. Repetition of objects is not allowed, and order is not important. So AB is the same as BA, and then again, our formula is given. If you look at the difference between these definitions, between permutations and combinations, you'll notice that everything is pretty much the same, except for order is important for a permutation, and order is not important for a combination. You'll also notice that the formulas are very similar too. Now for us, you don't really need to know the formulas because again, we're using our graphing calculator. But in other classes, you might have to know these, so it's a good idea to kind of look them over. So pretty much a permutation is the number of ways that you can select so many of them from a group, and that is where order is important for how you select them. So maybe it's when you're making a sandwich and you have a certain order that you want your, you have to have the meat first and you have to have the cheese next and you have to have this in a certain order, versus a combination, which is going to be where you're making your sandwich and you don't really care what order it's going to be put, all those items are put in. So next we have how to use our calculator, which we kind of saw already. And for this, give that a star. Permutations and combinations, then also factorials with the TI-83 or 84 calculator. So find your math button, scroll over to PRB or PROB, and you'll notice NPR and NCR and also that factorial. We'll get some practice on using that in just a moment. So next up we have permutations, when some items are identical to others, and the number of permutations of N objects in which N1 are of one kind, N2 of another kind, and so on. So Nk are of a kth kind is given by N factorial divided by N1 factorial times N2 factorial, so forth to Nk factorial. And so an example of this is, I remember going in and taking a test before getting hired at a retail store, and they had me take 100 question, I guess, survey, we can call it, to see what my responses were. And it starts off by asking different questions along the lines of, would you show up to work on time, and are you going to steal? And that are you going to steal one showed up later on, but they didn't word it the same, but it was still them probing to see if I would steal anything. And so there must have been about 10 of those questions on there, just worded a little bit different, but again, just trying to see if my response would have changed if they worded it a little bit different. And so that would be an example of this where you have permutations where some of the items are identical to others. So the next example says find the value of each using the calculator. And so I'm going to go ahead and work out this last column with you guys, and then I want you to try the other two columns on your own. And if you're stuck on those, definitely reach out to me or somebody at the TMARC or our tutoring centers to get some help. So the first one says 11 factorial. So for C, we're going to go ahead and type in 11. And then to get that factorial, we're going to select math, which is right underneath the alpha. Scroll over to PRB or PROB, depending on what your calculator says. Scroll down to factorial, select enter on that, and then select enter one more time, and we arrive at our answer of 39,916,800. And from the calculator, we get 39,916,800. And then going ahead and trying F, which is 9P9. So this means that you have 9 total objects, and P means permutation, so order is important. And so we're going to select 9 of those. For part F, calculators are going to work a little different. So it depends on your model of your calculator. And so some students are going to have to type the number first and then go to math, PRB, B, probability, and go down to NPR and then type your second digit. For me, for this version, I'm going to go ahead and select math, scroll over to PRB, go down to my permutation and hit enter. And you'll notice that there's little spaces there for me to type those digits. So the first one that I have is a 9. And then I'm going to scroll over to the other space to put my second little digit, which is a 9. And so I have 9, picking 9. And again, permutations is where order matters. Select enter. And I get 362,880. So from the calculator, we get 362,880. Part I is 9C9, and again that C stands for combination, so this would be 9 choosing 9 when order is not important, and if order doesn't matter, then you have 9 objects sitting there. Order doesn't matter which one goes first or not. Again, combinations are going to be a little unique for you also with your calculator, and you might have to type that first digit and then go to math in PRB, PROB, select combinations, and then type the second one. For me, I'm going to go to math, scroll over to probability, scroll down to combinations or NCR, and it gives me those little spaces down there to type in the numbers. My first digit is a 9, my second digit is a 9, and then selecting enter, I arrive at a nice answer of just 1. So from your calculator, you get 1. Now I'm going to go ahead and put the answers in for the other 2 columns, and again, definitely try these on your own to make sure that you can get these correct answers, and ask if you have any questions. The example next says, when designing a survey, pollsters sometimes repeat a question to see if the subject thoughtlessly provided answers just to finish quickly. For a particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. For the survey, how many different arrangements are possible? So we were given a formula before. First of all, it tells us that there's a total of 10 questions. This also tells us 2 are going to be identical, and then 3 others are also identical. And so we have 10 factorial, because that was the total number of questions that we had. And again, this formula is listed right up above. And then we have to divide by the ones that are the same, identical in some way. And so 2 of the questions are identical, and then 3 others are also identical. So 2 factorial and 3 factorial. And times, if you notice, it does say that N1 of one kind, N2 of another kind, and so technically you do have, this only accounts for 5 of those 10 problems. The other 5 are unique for themselves, so you can also divide by 1 factorial times 1 factorial 5 times. But 1 factorial we saw up above is only equal to 1. It's not going to change anything, so most of the time they just don't include that. On the calculator, I'm going to type 10 and then go to math, scroll over to that probability tab or PROB, PRB, and go down to my factorial key, select enter, and then I'm going to divide by, and I have 2 things in my denominator here, so I want to make sure I group those together. Some calculators will set it up more like a fraction, so you don't have this issue, but for me it does not. So I'm going to divide by 2, math, and scroll back over to probability, back down to factorial, times, and then 3, and then going back into math, PROB, down to factorial, and I have 2 times 3 factorial. And again, close your parenthesis, select enter, and you should arrive at the different arrangements that we will have, which is 302,400. So from the calculator, we get 302,400 different arrangements. The next example says, in the U.S. Senate, there are 21 members on the Committee for Banking, Housing, and Urban Affairs. 9 of these 21 members are selected to be on the Subcommittee of Economic Policy. How many different committee structures are possible for this subcommittee? So first thing is that with committees, it doesn't matter how you are selected to be on that. You are just part of the group of people that were selected. So it doesn't matter if you're the first person selected or the last person selected, you're still part of that committee. And so because of that, we know that order does not matter. Order is not important. And since order is not important, we know that we are dealing with a combination. And so I'm going to go ahead and put a C here for combination. And that first number that we have to put in, that little number that you put in at the bottom, is the total number of people that you would be selecting from for this subcommittee. And we had a total number of 21 people that we could select from. And then the second little digit that we put in there is the number that we are selecting. And so we are selecting 9 people. So we need to use our calculator to calculate this, or you can use the formula. But from the calculator, we get 293,930 subcommittees. The next example that we have says, in how many ways can the top 2 horses finish a 10-horse race? And so when we have races, we are dealing with order is important because it will make a difference if you come in first or if you come in second. So definitely anytime you have a race, order is important. I shouldn't say always, but almost always. There are some cases where maybe you have a race where everybody wins. So for this, since order is important, we are dealing with permutations. So I'm going to put a P there. Again, that first digit is going to be the total number of horses in the race, which is 10. And again, we're selecting the top 2. And so 10 picking 2. From our calculator, we get 90, and this is 90 different ways for any 2 horses to finish. And that's finished the race. The next example that we have says, suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting members of the Senate randomly. And so for this, we have a total of 55 Democrats and 45 Republicans. We are still dealing with a committee, which we talked about, where order doesn't matter with this. But part A says, find the probability that the committee is composed of all Democrats. So again, since we're dealing with a committee, I'm going to go ahead and put down order is not important. But I also want you to notice that we are dealing with probability, not just accounting. And I also want you to notice that this is a little bit more advanced than the other committee problem that we dealt with. That one was just finding a committee. This one has it broken into political affiliation. So we have so many Republicans and so many Democrats, and we're selecting so many, for this problem, all Democrats and no Republicans. And so we need to think about this and split this up into groups. And this is going to happen quite often. Things might be separated by age level, by gender identity, by race. So many different ways that we can separate things. But this is going to be the probability that, and it says that everybody on the committee is going to be Democratic. And they're going to be selecting 7 senators to be on this committee. So 7 are going to be Democratic and 0 are going to be Republican. And so in order to do this, first thing we need to talk about is our sample. And so our sample is going to be just looking at everybody in general. So I have 100 people here because if I add 55 and 45, I get 100. There's 100 different senators, and I need to select 7 of them. So combination, since it is a problem where order is not important, 100 total people selecting 7. And so that value is going to go into my denominator. So that denominator is the total number of ways that you can select 7 people, regardless of gender, regardless of race, regardless of political affiliation, just looking at how many different ways we can select 7 people. Now for this problem, it has it broken up into 7 Democrats and 0 Republicans that we want to select. And so I'm going to go ahead and write Democrats here and Republicans. And since this is a combination problem, I'm going to put a C above both Democrats and Republicans. And so for the first part, for Democrats, the total number of Democrat senators that we have is 55. And we are selecting 7 of those. For Republicans, we have a total of 45, and we're selecting 0 of those. And then it also has that connective word and, which is our multiplication rule. So go ahead and put a multiplication dot. So a lot of times for these problems, they'll ask you to set them up but not solve them. But for this one, we're going to go ahead and plug this all into our calculator and get an answer. For this problem, some students will choose to do each combination part separately and then put those numbers all in together. I'm going to go ahead and do the numerator first. And so I'm going to put a parenthesis here since I have multiple things here. And I'm going to go ahead and say math and go over to my probability. Go down to NCR, which is my combination. That first one that we have is 55. Choose 7. And then I need to scroll right and put times. You want to make sure that times is not written right next to the 7, that it's next to the C. And then we're going to do the same thing, go into math, go over to that probability tab, go down to combinations, select enter again. First digit here is going to be 45 and we are choosing 0. And then I need to close my bracket. So that was all of my numerator, and I'm going to divide all of that by, and I need to divide it by that 100, choose 7. So I need to go into math, go over to probability, go down to NCR. First digit is 100, and we are choosing 7. From here, we're going to go ahead and select enter. And again, you could do each of these individually and put the numbers in. And when you get this, you get a decimal. We are going to be rounding our probability answers to 4 decimal places usually. So we'll say round it to 4 decimal places. We get 0.0127. So working this out on your calculator, you get an answer of 0.0127. Part B says, what is the probability that the committee is composed of 3 Democrats and 4 Republicans? So probability that we have 3 Democrats and 4 Republicans. So our sample is still going to be the same. It's 100, choose 7. So that denominator is not going to change. And again, Democrats and Republicans, we're going to put a C above both of these. We have a total of 55 Democrats, and this time we're going to be selecting 3 of them. For Republicans, we have a total of 45, and this time we will be selecting 4 of those. And again, that multiplication rule, and again, they're independent, so we can multiply those together. So substituting this all into your calculator, we arrive at 0.2442. Also, a way to check to see if you did this correctly is if you look at the numbers all to the left of C, you'll notice 45 plus 55 would equal 100. And also 3 plus 4 would equal 7. Likewise, it works also for those. The last page here is page 10. And this page has a few problems just kind of thrown in here for us to look at. Most students do well when they know how to start the problem. However, they never tell you how or what to do for the problem. It's your job to read them and understand what they're asking, and that could be a challenge for many students. So there's 3 different problems here to try. My suggestion would be to try these on your own first, and then continue on watching the video. So if you want to pause it and then see if you can work these out on your own and then check and see how you did. But if you want to sit and work these out with me, feel free to do that also. So definitely ask if you have questions. So this example says, through a manufacturing error, 3 cans are marked regular soda are accidentally filled with diet soda and placed into a 12-pack. Suppose that 3 cans are randomly selected from a 12-pack. Part A says determine the probability that exactly 2 contain diet soda. And so for this, we're selecting cans, and we're going to select 3. It doesn't matter which ones you select, the order that you select them, so order is not important. And I know that there's a total of 12 cans. I also know that there's going to be 3 that are diet, and that means that 9 are going to be regular soda. So for my sample size here, it is a combinations because order is not important. And again, remember, we don't care if it's diet or regular, political affiliation, anything like that. It's just the total number of cans that we'd be selecting from, which is 12. And we're selecting a total of 3. So that's going to go in the denominator. But this question, part A, says, what is the probability exactly 2 contain diet? So this is about that 2 contain diet. And since we're selecting 3 cans, it's going to be 2 are diet, and that other one is going to be regular soda. So again, in the denominator is going to be 12, choose 3. And then we have diet and regular. Putting a C above both of those. The total number of diet cans that we have in that 12-pack is 3. And we're going to be selecting 2 of them. And the total number of regular sodas we have in the 12-pack is 9. And we're going to be selecting 1. Again, putting a dot for multiplication. So on our calculator, I'm going to go ahead and enter in all of this at once. So I'm going to go ahead and put some parentheses around my numerator, go into math, go over to probability, and then I need to go down to combinations. My first one is going to be 3, choose, and we are choosing 2 diet. Scrolling right, hitting my multiplication dot, going back into math, going down to my NCR, which is my combinations. First digit here is a 9, and we're selecting 1 of those. Close my parentheses, and then divide by my sample space, which again is going to be math. Go over to probability, NCR, and we'll be selecting 12 cans, or there's a total to select 12 from, and we're selecting a total of 3. So from here, I'm going to go ahead and select enter, and I get my decimal answer. Again, this is a probability. Rounding 4 decimal places, we get 0.1227. Rounding 4 decimal places, we get 0.1227. Part B now says determine the probability of exactly 1 containing diet. So this would be 1 is diet, and if 1's diet, that means that 2 are going to be regular. So our denominator is going to be 12, choose 3, and we have diet and regular, put a C above both of those. The total number of diet cans that we have in our 12 pack is 3, and this time we're selecting 1. And then regular, we have a total of 9, and we're selecting 2. Get multiplication. Then substituting this all in on your calculator. Some students will find it easier to calculate each of these combinations independently and then plugging those values all in on your calculator. But running 4 decimal places, we get 0.4909. And then part C says determine the probability that all 3 contain diet. So this would be the probability that 3 contain diet and 0 are going to have regular soda. So again, our denominator is still going to be 12, choose 3, that's our sample. And so going ahead and putting diet here and regular with a C above both of those. We have a total of 3 diet cans and we're selecting 3 of those. Whereas we have 9 regular cans and we're selecting 0 of those. And so then working this out, we get an answer of 0.0045. The next example right below this says, suppose that you have just received a shipment of 100 TVs. Although you don't know this, 6 are defective. To determine whether you will accept the shipment, you randomly select 5 TVs to test them. If all 5 TVs work, you're going to accept the shipment. Otherwise, the shipment is rejected. What is the probability of accepting the shipment? So for this, you're going to select 5 and you're going to test them. So order is not important. And so we know that we have 100 total TVs. We also know that 6 of these are defective. And if you had 100, 6 of them defective, we know that 94 of them are going to be good TVs. So our sample here, putting a C for our combinations. Again, it doesn't matter if you're good or defective, it's looking at all TVs the same. We have a total of 100, and it does tell us that in order to accept this shipment, we have to test 5 of them. We're going to select 5 and test them. So we're going to choose 5 of those TVs. And it says, what is the probability of accepting them? And it says that it will only be accepted if all 5 TVs work. So all 5 are going to be working TVs or good TVs, and 0 are going to be defective. Since we're dealing with our probability, our sample space is that combination of 100, choose 5, and that's going to go down the denominator. And then we have good and defective TVs, which each get a C. And the total number of good that we could select from is a total in that shipment is 94. And we're going to select 5 of those. And defective, we have a total of 6. And we'll select 0 of those. And then multiplication there equals. And then working this out on your calculator, you get 0.0045. There's one more example here. And this one says, Todd is putting together an exercise routine and feels that the sequence of exercises can affect his overall performance. He has 12 exercises to select from, but only has enough time to do 9. How many different exercise routines could he put together? So one quick thing to note here is that he feels that the sequence of exercises can affect his overall performance. So to Todd, order matters. So order is important. And since order is important, we know that we are dealing with permutations. So I'm going to go ahead and put P for permutations. And then for this, we have a total of 12 different exercises that he can do, but he only has time to do 9. So 12 would go first, and we're going to pick 9 of those to do. And so then working this out and substituting this in on your calculator, we're at 79,833,600 exercise routines. A lot of times students struggle with this chapter, and it's a good idea to get some extra practice. An additional place to look to get some extra practice would be in our textbook, and at the end of each chapter there are some additional exercises that you guys can look at, or you can look at the examples that are done in the textbook